Okay, now we're going to talk about zero force members. Sometimes with trusses, redundant members are added and they carry actually no load. For example, this truss is supported like so, a roller here, and a pin here. And we have a load of P here. Okay, this truss has a number of elements that are redundant and actually carry zero load. See if you can guess which ones they are. So if you look at this truss and we sum forces, say we sum forces about A equals 0, or we look at actually pin A and we sum forces about X, we're going to see that force AC, let me draw a free body diagram. Okay, with the free body diagram, this clears it up a lot. So if we sum forces in the X direction, then we've got force AC and nothing else. So therefore, force AC equals 0 and drops out. If we sum forces in the Y direction, we get force AB equals 0, and therefore force AB also drops out. So both of these are redundant zero members, zero load members. Over here, we can do the same thing. Let's assume F FE is vertical. It's not drawn very well, but assume it is. And it's not really even necessary. But if we look at pin F, we see that if we so I redrew that so this would look a little easier for us to understand. So pin F, we have a force in this way and a force in this direction. So let's just say there's a theta here. So if I were to sum forces in the Y direction, or better yet, let's sum forces in the X direction equals 0. So I've got FD. Let's call that sine of theta. Well, since sine of theta equals something here, don't know what exactly because I don't know what that angle is, but I know it equals something. It doesn't equal 0, that's for sure. Since this is not equal to 0, that must mean that FD does equal to 0. FDF, really. So this equals 0. Now if I go ahead and sum forces in the X direction equals 0, or in the Y direction, I have minus force FE and that's it, since this one equals 0. So force FE also equals 0. So we have 4 elements in this that are redundant. And we can take them out for analysis purposes and just analyze the structure without those in it. So that could simplify. If you notice where your zero force members are in a structure, it can make solving the structure easier. Okay, let's analyze this. This is example 6-16 in your book. These are 60 degrees here and 60 degrees here. Also, this distance and this distance, those are 4 meters. And this is also 4 meters from here to here. So because of this symmetry, what it turns out is all these angles are 60 degrees. And that's if you assume that this top line here is horizontal. So I think that's an assumption you need to make. Well, it'll make our job a little easier before we start analyzing the internal stresses. And we could just jump in and start analyzing the internal stresses because point D is an analyzable point. And we can move from point D to point C and then go around to B and then just circle around and we will get everything. But I'm going to go ahead and I'm going to solve for my reactions first. Here's a quick little free body diagram of the structure. So sum of forces in x equals 0 equals ax, therefore ax equals 0. We could sum moments about E equals 0. This will lead to, you can go ahead and do that, this is going to lead to AY equals 8, and then if I sum forces in the y direction equals 0, then we end up with EY equals 16. So EY points in this direction, AY points in this direction, and there we go. Okay, starting out at pin A, I have 8 kilonewtons down, and then these 2 element forces. So always start out with them in tension. So F, sum of forces in the y direction equals 0 equals minus 8 times or plus F A B. The what is that sine? Yeah, sine is 60. So you got to keep your angles correct. So F A B ends up equaling 9.237 and kilonewtons. All right, I like to box these as I do them. Okay, here we go. Sum of forces in the x equals F AE plus FAB cosine 60 degrees. So FAE equals minus 9.237 cosine of 60 degrees. So FA equals minus 4.619, which means it'll be in compression. It'll be causing compression. Let's move on to pin D over at the other side of the structure. For pin D, we have a free body diagram like this. Notice I drew the reaction in the correct direction, but I drew the forces on the pin, always assuming tension, and we'll find out what they turn out to be. So sum of forces in the y equals 0 equals minus P plus F CD sine of 60 degrees. So therefore F CD is going to turn out being 9.237 kilonewtons. And if I sum forces in the x on this pin, equals minus FCD, or minus FED, not FCD. Oops. Minus, so these are both pointing in the negative direction, minus FCD cosine 60 degrees. I can plug 9.237 in here, so half of that, because that's cosine 60. So FED is going to end up being, well, this will come over here and be positive, but it's still going to be negative, but it'll be negative half of CD. So it's going to be minus 4.62. Okay, so we've solved for this one, this one, this one, this one. We only got 3 more to do. Okay, let's work on pin C. So I've got a force CD. I've got another force CE. And then I've got a force in this direction, BC. So I have this one. So I'm able to solve for these two now. So you always want to choose a pin where you can solve something in your next choice. And so this guy works. Pin C works for me. If I sum forces in the Y equal to 0, I get minus P. Oops, mistake, not minus P. I get minus force in CD times the cosine of 60 degrees minus my force CE times the cosine of 60 degrees. That's it. So we can cancel these, and I can end up with FCD equals minus FCE. Let me do that again. So I canceled those, so I know that FCD equals minus FCE, and that means that force in CE equals the negative of that, which is minus 9.237 kilonewtons. Now, as I sum forces in the x direction, I end up with minus force BC minus force CE times the cosine 60 degrees. Is it the cosine 60 degrees? Yeah, these are all 60 degrees. Minus or plus the force in CD times cosine of 60 degrees. So this equals minus force in CE, which is minus times the cosine of 60 degrees, plus force of CD, which is positive, times the cosine of 60 degrees. So it's two positives cosine 60 degrees, and cosine 60 is 1/2, so it's 1/2 of that number, which is 4.62 kilonewtons. But it's 1/2 twice that number, which ends up being 9.237 kilonewtons. So okay, now I get this, and I get this. And it's just a simple matter of doing this last calculation at B, or using symmetry to figure this out. Either way, the force in BE, you're going to have to calculate it, equals minus 9.24, because I don't have time.